All right, guys, 1.6, exponential functions. Probably a new topic. I don't think this is something that you have worked with in any previous classes. Now, an exponential function, we're not going to get into the exploration stuff here in the video, but an exponential function is a function where the x value is in the exponent. So it's something like f of x equals 2 to the x, or f of x equals 0.75 to the x. So the x is not in the bottom. The x is up in the exponent. That makes it an exponential function, all right? A couple of things that you need to know going into this. Really, we don't need to worry about too much of this previous stuff. We'll cover it all through our examples here. So let's talk about exponential growth and the exponential decay functions, okay? So like I said, an exponential function, I'm just going to read through this little bit of information up here with you, okay? An exponential function has the form y equals abx. So it might be y equals 3 times 7 to the x value. This number in front, this a value right here, it can't be 0. If it's 0, then the entire function turns into y equals 0. So that's why it says a cannot be 0. And then it says the base b is a positive real number other than 1. Okay, and I'll show you an example here in a little while why it can't just be 1. So exponential growth happens if a is not 0 and b is greater than 1. Okay, so if a is greater than 0 and b is greater than 1, then you have what's called exponential growth. So if you have something like y equals, and really, guys, we're not going to use a very often except for in the story problem. So if y equals 4 to the x, this is exponential growth. If y equals 1,324 to the x, that is exponential growth because my base value is bigger than 1, okay? So this is an exponential function. Well, okay, if I write it like this, f of x equals 1,324 to the x, that's an exponential growth function. And this value right here, the base, we call the growth factor, okay? That is telling you the amount that you're growing. That's the growth factor. Instead of staying the same all through time, it's telling you what percentage you are growing, okay? And again, we'll get into some more detail of that a little bit later. So the base form of this, the parent function looks like y equals b to the x value. Okay, that's what the parent function looks like. When you graph it, this is what it looks like on a graph. So a couple of things I want you to notice. As I go to the right, I go through the point 0, 1. Okay, unless my function is getting shifted, I am always going to go through 0, 1. Because the reason that happens is, if you remember when we were talking about the rules of exponents, it doesn't matter what my number down here is. If it has a 0 up here, my answer is 1. That's why the point 0, 1 is always on this parent function graph, okay? And that's one of the points that you're going to graph today. One of the other important points is 1b. This is another point that it always goes through. Whatever your base is, whatever this value is right here, that is going to be your y value when the x is 1. Which again makes sense because y equals 7 to the first power equals 7. So that's always going to be another point on your graph. And then from there, my exponential function shoots up really, really, really fast. Okay, it gets really steep really fast. When I go to the left, it looks like I go to 0, but there's actually an asymptote, all right? I never cross this y equals 0 line. I never reach 0. I get really, really, really close to it, infinitely close to it, but I don't actually touch it. And that's why when you look at the domain, my domain is all real numbers. I go to the left forever, I go this way forever, and I go to the right forever. I go up forever, but I never go below 0. In fact, I never even reach 0. So my range is y is greater than 0. All right, couple of things there to keep in mind as we're going through these problems today. Now, what happens if my b value is not greater than 1? Let's say I have a b value, something like y equals 0.5 to the x, or y equals 0.001 to the x value. This is called an exponential decay function. Your function is getting smaller and smaller and smaller over time. Instead of growing really fast, which you want your savings account to do, this function gets smaller and smaller over time, which is what you want something like sicknesses in the world, or virus counts, or cancer loads. Those are things that you want to get smaller and smaller over time, right? So if this value is smaller than 0, I have exponential decay. If it's bigger than 0, I have exponential growth. Now this function right here is my exponential decay function. I still have the point 0,1. I still cross at 0,1. Whatever my b value is still where my x equals 1. That's still a point on the graph. And from there, the opposite happens. As I go to the left, I get really, really steep really fast. As I go to the right, I get closer and closer to 0, but I don't ever actually cross 0. I just get really close to it. Okay, enough chatter. Let's do some problems. Example number 1. Determine whether each function represents exponential growth or exponential decay. All right, first of all, ignore all the solution stuff down here, okay? We're going to make our own notes in our notebook. We're going to do the same thing, but we're going to do it in a lot easier way, okay? We're going to do this a lot easier way than all the steps that they have here. So it tells me, it wants to know y equals 2x. Is this a growth or decay? So step 1, here's what I want you to write in your notes. You're going to add this little thing to your notes right here. Not to your book, to your notebook. You're going to say step 1 is you need to ask yourself a question. Is the base bigger than 0 or less than 0? Is my base, is this value right here, bigger or smaller than 0? Now, in this example, it is bigger than 0. And if you remember, that means exponential growth. So if b is bigger than 0, then it's growth, and it looks like this. If b is less than, not 0, what am I doing? If b is greater than 1, bad math, Mr. Reed. Is the base greater than 1 or less than 1? If b is greater than 1, then it's growth. If b is less than 1, then it's our decay function. Okay, sorry, I'm getting ahead of myself and I'm using the wrong values. Now it wants you to make a table. So based on this, I know that my function is growing, but it also wants me to graph the function, okay? Now, if I know my function is growing, I know that it looks like this, right? Kind of like that. It's not going to go to 0. It's going to get close. There's only 2 values I care about. I don't care about -2. I don't care about -1 or 2 or 3. The only values we care about are these 2 right here. What happens when x is 1 and what happens when x is 0? You know what happens when x is 0. My y value is 1. Okay, when x is 0, my y value is always 1. You don't have to find all the other values. That is one of them that you need to find. The other value is when x is equal to 1. Do you guys remember what your y value is? Your y value is just the base. So when x is 1, I go up 2. These are the only 2 points I care about you graphing. From there, I want to see a smooth curve. I want to see it go through these 2 points and then get really steep. And I want to see it come to the left and get close to 0, but I don't want to see it cross 0. I will tell you right now, if it crosses 0, I will not give you credit for this question. If it crosses that line, you're not going to get credit, even if you tell me it didn't mean to cross the line. If on your picture it crosses, you don't get credit, so be really careful of that, okay? And that's it. That's my whole graph. So ignore all these other steps. Let's do B. So B said y equals 1/2 x. Okay, step 1. Is the base greater than 1? No. My base value is less than 1. It's a half. So that means this is a decay function, which means it's going to look like this. It's going to get smaller instead of bigger as I go to the right. So let's graph it. Okay, I don't care about -3. I don't care about -2. I don't care about -1 or 2. All I care about is 0 and 1. 0, I already know the answer. It's right there at 1. 1, if I were to get a 1, if I were to plug in a 1, my y value is the same as my base. So my y value is just a half. So if I go over 1, I go up a half. Now I can graph it. As I go to the right, I want to get close to 0, but not cross 0. As I go to the left, I want to get steep really fast. That's all I'm looking for. That is enough detail that I'll give you full points on that graph right there, okay? So here's what I want you to do. I want you to try these 4 all by yourself, okay? Step 1, is it a growth or a decay? Look at the base value and then graph it for me. So pause the video, take 2 minutes and graph these 4 functions. All right, so number 1, what you should have gotten, your base, my base is equal to 4, so that means this is a growth function. It's going to look like this. So when I graph it, all I care about is the point 0, 1, and 1, up 4, 2, 3, 4. Ta-da! Now as I go to the right, I'm going to get steep really fast. As I go to the left, I am not going to cross y equals 0. You can get as close as you want, but you better not cross it. Okay? All right. Number 3. Y equals, I don't care. We're doing number 3. F of x equals 0.25x. Okay, my b value is 0.25. That is less than 1. So this is a decay function, which means it's going to go down. So when I graph it, I care about the point 0, 1. And my other point is based on that base right there. I'm going to go over 1 and I'm going to go up 0.25. So as I go to the right, I'm going to go through those 2 points and I'm going to get really close to 0. As I go to the left, I'm going to get tall and steep. That's all I want to see. One thing I did get asked last year. Yes, I care that these 2 points make sense, okay? Just because you know it's a decay, I want your point to be kind of realistic. Don't just give me a graph and go like this, okay? I want to see that you've marked at least those 2 points. It's not a lot to ask to see. So take the time, do it right, so I can give you credit for it. Okay, number 2 over here. Now you guys feel better, right? Because now I'm doing number 2. My b value is 2/3, which is less than 1, which means this is exponential decay. So when I graph this, I'm going to go through the point 0, 1, and then I'm going to go through the point, I'm going to go over 1, and I'm going to go up 2/3. So as I go to the right, I'm going to get close to 0. As I go to the left, I'm going to go to infinity. And I'm done with that one. I told you this is an easy day. Nope. Here we go. All right. Number 4, my b value is 1.5. That is greater than 1. So this is an exponential growth, which means it should look something like this. So when I graph it, I'm going to mark 0, 1 on the graph. The only other point I care about is over 1, and it's going to go up. If this is 1 and this is 2, I'm going up right in the middle. And as I go to the right, I'm going to grow steep. As I go to the left, I'm going to get closer and closer and closer to 0. But my line is not going to cross it because I want credit for this question, okay? All right, writing exponential models and recursive rules. Don't do this in your book. We're not going to cover recursive rules. We're not going to do that this year. I don't think it's necessary, and we don't want to take the time to do it. So we do want to talk about exponential growth models and exponential decay models, okay? So these are 4 story problems. The reason we are covering this version, the reason the exponential growth model y equals a times 1 plus r raised to the t, this is all about story problems, okay? I can't just use y equals b to the x to solve every story problem, but I can use this function. It's the same function, it's just written a little bit different, all right? Here's what I want you to know about this function. Actually, this is all written down below for you. But in your notes, maybe this is something that, well, not maybe, you should definitely add this to your notes. So add this right here. Pause the video, add that to your notes. And then I'm also going to have you add that A represents my initial value, whatever I started with. That is A, all right? R, the letter R is going to represent my percent increase or decrease as a decimal. So if I go 5% up, my R is going to be 0.05. If I go 100% up, my R is going to be 1. If I go 25% down, my R is going to be 0.25. And the t value is the number of years as time has passed. Most of the time, that's what it represents, okay? The only difference with exponential decay is we're not growing every year. So instead of a plus in the middle, we're decaying, so there's a minus in the middle. So let's do a problem. Example number 2. The population of a country was about 6.09 million on January 1st, 2000. The population at the beginning of each subsequent year, do you know what subsequent means? That means following. Okay, the population at the beginning of each of the following years increases by about 1.18%. Okay, numbers that I care about. 1.18%, 6.09 million so far. Write an exponential growth model that represents the population, y, in millions. In millions means don't write. When it says 6.09 million, when it wants the answer in millions, it means please don't do 6,090,000. Anyway, it doesn't want you to write it like this. It wants you to write it as 6.09 million. It wants me to write an exponential growth model. And then it wants me to use that model to evaluate what happens when t is equal to 7.5. That's part A. Part B wants me to estimate when the population is 7 million. And that's a little bit harder to do because I got to show you how to do something on the calculator. So first things first, we want to write an exponential growth model, okay? Now, in your book, I know this example's here. I want you to follow through it with me, though. My A is 6.09. My R was 1.18%. So to get that as a decimal, I take my 1.18 and I move the decimal 2 places. Nope, wrong way. Sorry, guys. I move my decimal 2 places this way. And I get 0.0118. Okay, we're not making it a percent. We're making it a decimal. So when I write my function, y equals, and I don't care if you do f of x or y equals, I'll accept both of those. Y equals, A goes first, 6.09. And I know that's millions, but right now 6.09 is good enough. And then a parenthesis. And then my formula says to do 1. Now, my population is increasing every year. So this is going to be a plus because I'm going up 0.0118%. And then I put t up here for the number of years. That's my exponential growth model. I just plugged in the values, all right? Then it wants me to find out, well, what happens when t equals 7.5? So in my calculator, I'm going to type 6.09, parenthesis 1 plus 0.0118, parenthesis 7.5. You're going to plug that in your calculator, but you're going to write that on your paper. I don't expect you to solve that in your head, but I want to see that you wrote it on your paper before you typed it in your calculator. Then you're going to say, Mr. Reed, that equals, I don't even remember what it equals. What does it equal? Where is my answer? Down here? There we go. Approximately 6.65 million. So that is approximately 6.65 million. So 7.5 years later, I was at 6.09 million. 7.5 years later, I'm at 6.65 million people. If I'm growing 1% per year, that's a lot more people. We're 500,000 more people than we were just 7 years ago. Now, part B. Part B is a little bit harder because it wants you to find a time. It wants you to know when, what year, what time, what hour. When is the population about 7 million? Now, here's the issue. My function looks like this, 6.09, 1 plus 0.0118 raised to the t. It wants y to be 7 million. It wants to know what t value will give me that answer. And here's how you do it on the calculator, because that's not something you know how to do without a calculator yet, okay? But the little calculators that you have here in class will do this for you. What you're going to do is just like they did here in the book, you're going to make a table. But on these calculators, you need to know how to make a table. So step 1, hit the table button. Ta-da! Weird. You make a table by hitting the table button. Step 2, you're going to scroll down to where it says edit function, and you're going to hit enter. All right. Step 3, you are going to type, actually f of x is already there. The part that you're going to type is this part right here. 6.09 parenthesis 1 plus 0.0118 raised to the x. That looks familiar, right? Yes, that's your function. Then you're going to hit enter, and you're going to go down, and it's going to ask you, it's going to make a table for you, but it's going to ask you, where do you want to start and how much do you want? Like when it says step, it means, do you want to count up by ones? Do you want to start at 1 and go 1, 2, 3, 4, 5, 6? Because then you would make this step a 1. Do you want to start at 10 and count by tens? Then you would start at 10 and your step would be 1. You would go 10, 20, 30, 40. So it's going to ask you to put in values where you want to start and how much you want to skip each step. So start at 1 and skip 1, all right? And then you're going to click enter, and it's going to take you to a table. When you get to the table, you're going to see something like this, X, Y, and it's going to start at 1, and it might only have 2, and it's going to give you values right here. We want our population to be 7 million. So you are looking for this number on the right to become 7 million. Well, technically 7.0, right? So you want this to become 7.0. So you're going to scroll down until the Y value is 7 million. And that's going to give you a X value when that happens. I know it's in our function, it's a T, not an X. All it is a variable. Just know that the x and the t mean the same thing, okay? All right, recursive rules. We're not doing recursive rules. We're skipping that one. So ignore all of that. Don't cross it out in your book. Just ignore it, skip it. Example 3, ignore it, skip it. Example 4, ignore it, skip it. I'm way too nice. Oh well, I'm sure you won't mind. Okay, so let's do a couple examples. Number 5, solve a real life problem. The value of a car is $21,500. You lose, oh, that's such an important word. You lose 12% of its value every year. Question A, write a function that represents the value y in dollars. Okay, so y equals, what goes first in my exponential function? My starting amount. So 21,500 parenthesis 1, and I'm losing 12%. So I'm going to do minus. Now 12% as a decimal becomes 0.12. So I'm going to minus 0.12, and then I'm going to raise that to the value t. All right. Simplify. Don't worry about simplifying. That right there, well, I guess this number on the inside, we could simplify that. 21,500 on the outside. 1 minus 0.2 becomes 0.88 raised to the t. So what that means is every year, my value is going down 12%. So my new value is only 88%. That's what it means to do 1 minus 0.12. So, part B is a weird question. We haven't done part B yet. It says, find the approximate monthly percent decrease in value. Okay, monthly percent decrease. And it has some instructions right here for you. I'm going to show you where that came from, okay? So our original function looks like this. Now you're going to have to be able to do this yourself. I'm going to rewrite this because this is t is based on years, but I want to change it to months. So instead of t being years, I'm going to change that to 12t, and now that's going to represent months. But that's a problem. I can't just change that to a 12. If I change that to a 12, this one on the inside, I have to change to a 1 over 12, right? Because isn't 1 over 12 times 12 just 1? So I'm just rewriting this to change it to a monthly value instead of a yearly value. So this 0.88 to the 1/12, I don't even know what that is. What is that in your calculator? 0.88 raised to the 1/12 is 0.989. So my y is going to become 21,500 times 0.989 raised to the 12t. So instead of t representing years, now t is representing what? Right? We turned it into months. So that's what the 12 did. We just took our problem and we turned it into months instead of years. So part C wants me to do what? Part C says, part B asked for our decay factor, right? Didn't it? It asked for something. Find the approximate monthly percent decrease. Okay, so 0.989 is my new decay factor. And if you remember, 1 minus my rate equals 0.989. So if I get my rate by itself, that becomes 1 minus 0.989. So my rate is going to equal 0.11. So I'm going down 1.1% a month. All right? I'm going down monthly 1.1%. I'm not going up, I'm going down, okay? Part C, it wants you to graph. Again, I only care about two values, so when you graph this, there's two values I want you to plug in. You don't have graphing calculators, so this isn't something that you're able to graph. So part C, you can just do on Desmos, and I'll actually show you how to do that in class because we're not able to do that here with your little, or you're not able to do that at home with your little calculator. So I'll show you how to do part C in class. And number 4, we'll talk about that one a little bit more in class as well. So don't worry about parts C and number 4. We'll do that together in class. What I want you to do for your homework is 3 through 17 odd, 21 through 22, 41 to 46, and then number 65 and 69. Remember, the stars don't mean only do it if you want. The star means they're going to be a little bit challenging, but I want you to try them. Maybe I'll just take the stars off. Maybe the stars is making you just not even try. I don't know. But try them. It's good for your brain.